Okay, so let's talk about isotopes, and then we'll talk about how we calculate what's called average atomic mass. So we defined what an isotope was in the previous video, but again, what an isotope is it's an atom, it's the same atom, and it has different numbers of neutrons. So it's the same atom, so that means it has the same number of protons, but different numbers of neutrons. So let's just look at an example. So carbon 12 and carbon 14, for example. So when we're talking about isotopes, we would say carbon 12 and then carbon 14. So carbon 12 and carbon 14, these are isotopes of each other. So carbon 12 and carbon 14 are both isotopes of carbon. Carbon 12 would look like this. So the word 12 here, this gives me the atomic mass. So carbon, I know, is number 6 on the periodic table because it has 6 protons. Remember, the protons never change, but it has an atomic mass of 12. So that would be the nuclide for carbon 12. Carbon 14 would look like this. Carbon 6, but then up here for the atomic mass would be 14. So this is carbon 14 and this is carbon 12. They are isotopes of each other. Let's just talk about the protons, neutrons, and electrons. Carbon 12 has 6 protons. It has 6 neutrons, and because it's an atom, and remember atoms are always charge neutral, it has 6 electrons. So let's look at the subatomic particles for carbon 14. Carbon 14 still has 6 protons because all carbon has 6 protons. Remember, the protons, the atomic number, that gives an atom its identity. So nothing with 6 protons can be anything other than carbon, and you can never have carbon that doesn't have 6 protons. This one has 8 neutrons because remember, the atomic mass up here is the sum of the protons and the neutrons. So that means I must have 8 neutrons. And again, because it's still a charge neutral atom, it still has 6 electrons. So the difference in these two is the number of neutrons. That's it. Carbon 12 has 6 neutrons, carbon 14 has 8 neutrons. So you notice when you look at the periodic table, there are atomic masses on the periodic table, and usually it's underneath whatever element symbol you're looking at on the periodic table. And you'll notice that these are not whole numbers. Well, you can't have part of a proton or part of a neutron, so how come the atomic mass on the periodic table are not whole numbers? And the reason for that is the atomic mass on the periodic table is really what's called the average atomic mass. And it's really the average of all the masses of the naturally occurring isotopes of that element. So for example, when you look on the periodic table, your periodic table might look something like this, where you have a carbon, and then up here at the top it says 6, that's the atomic number, and then down here it might say something like 12.011 or something like that. Well, in your periodic table, it might look like this, where up here, now this is the atomic number, and down here, this is the atomic mass. And all periodic tables are set up a little bit differently, so if yours doesn't look exactly like this, that's totally fine. But this is the atomic mass. Well, we said that the atomic mass is the sum of the protons and neutrons. The subatomic particles, these are the smallest particles that we can have. So how can we have an atomic mass that's not a whole number? Because this atomic mass is the average atomic mass. It's the average of all the isotopes of carbon. So you'll notice that the average is very close to 12, which means carbon 12 is the most prevalent naturally occurring isotope, but there is some carbon 14, so when you average together the amount of carbon 14 and the amount of carbon 12, that small amount of carbon 14 is going to increase that average atomic mass just a little bit. So let's do an example of calculating average atomic mass. Okay, so let's say that there are 2 isotopes of nitrogen. And we'll say it's nitrogen 14 and nitrogen 15. So the naturally occurring abundance of nitrogen 14 is 99.4%. And the naturally occurring abundance of nitrogen 15 is 0.6%. So now the question is, what is the average atomic mass of nitrogen? Okay, so this is a weighted average. So nitrogen 14, having an atomic mass of 14, has 99.4% of the naturally occurring nitrogen, and then nitrogen 15, having an atomic mass of 15, has a naturally occurring abundance of 0.6%. So this is a weighted average, and the unit here is AMU. Atomic mass unit. So what I'm going to do is I'm going to take the percent abundance, I'm going to multiply it by the mass of that isotope, and then I'm going to add the two together. So I'm going to say, remember this is a percentage, so when you multiply by a percentage, you divide by 100, because remember percent, cent means 100, percent means out of 100. So I'm going to say 0.994 times the mass, 14 AMU, plus, remember, percent, so out of 100, divide by 100, 0.006 times the naturally occurring abundance of nitrogen 15, 15 AMU, is going to give me the average atomic mass. So I'm going to say 0.994 times 14 plus 0.006 times 15 gives me 14.006 AMU. So this problem does not really include significant figures. Let's say we're going to report the atomic mass to 2 decimal places. So you would look 1, 2 decimal places, you look over. So the correct answer here, if we were reporting it to 2 decimal places, would be 14.01 AMU is the unit. So you multiply the percent abundance times the mass of that isotope, and then you add those masses together for each of the isotopes to determine the average atomic mass. Let's do one more. I'll give you a table this time. So now let's say we are calculating the average atomic mass of neon. So there are 3 naturally occurring isotopes of neon. There's, so here we'll say isotope, and here we'll say percent abundance. So the isotope, there's neon 20, neon 21, neon 22. So the naturally occurring abundance for neon 20 is 90.48%. For neon 21, it's 0.27%. And for neon 22, it's 9.25%. So let's say again, let's report our answer to 2 decimal places. Okay, so I'm going to do the same thing. I'm going to take the mass, I'm going to multiply it by the percentage. Remember to convert the percentage to a decimal by dividing by 100. So that's what I'm going to do here. I'm going to say 0.9048 times 20 plus 0.0027 0.27%, yeah. 0.0027 times 21 plus 0.0925 times 22. And then I'm going to give my answer to 2 decimal places. So I'll say 0.9048 times 20 plus 0.0027 times 21 plus 0.0925 hang on, let me do this again. 0.9048 times 20 plus 0.0027 times 21 plus 0.0925 times 22. And I'm going to report this to 2 decimal places, so I'll look 1, 2, and then I'll look at the next one, and it's 5 or above. So I'm going to say 20.19 AMU. That's the average atomic mass of neon based on the relative percent abundances of these 3 neon isotopes. So when you look at the periodic table, you'll see that these average atomic masses are not whole numbers. And you'll even see if you look at one periodic table maybe from like 10 years ago and then a periodic table today, the average atomic masses for elements might be a little bit different. And that's because the average natural abundance of these different isotopes are always changing. So that's why you have different masses on different periodic tables. It depends when they were published. Whenever you're using a periodic table in this class, you always will get an answer that is close enough so that when you round to the correct number of significant figures, your math will always be correct. But just don't be confused if you see different periodic tables that have a little bit different average atomic masses, because the average atomic masses always comes from the average of the atomic masses of all the naturally occurring isotopes of that element.